Okay, let's move on to beams and deflections, and let's have a look at the problem sheets. So first thing to note is that if you go onto the Dropbox, you would be able to click, I think, tutorial questions. Oops, go back one, in-class questions. Oops, go back, sorry, tutorial questions. And then you would see that this one here is BDB1, which you can see there, BDB1. If you click BDB1, you will get some solutions. So you could click that solution and then you could see how I've drawn it out. And then you could click that one, which says it's a YouTube solution, which doesn't mean much. It just means that I've given you a link to a YouTube video, which you could click there, and then I would be explaining it in a bit more detail. Okay. So solutions for all of these can be found on the Dropbox. So let's have a look at the first one. So the first one would be a simply supported beam. So obviously that one is obviously a pin, and that one is meant to be a roller. Sometimes engineers are not that precise because they just assume that it's obvious what it should be. So we've got the pin and we've got the roller. Just give me a second. Pin and roller, pin and roller. Cool. So down here you would see pin and roller. That's a pin, can't move in the up direction, left to right, and then the roller can't move in the up and down direction, but it can move left to right. It's got a central load on in the center, so you can see when you apply that, the roller end actually comes in. Okay. Let me just get this one here, that would be better. Sorry about that. So pin and roller, and then when you see it, you can see both ends are rotating inwards under that load. So when you draw the bending moment diagram, firstly that's a 50 kilonewton force. So you would know that each end would be 25 kilonewtons, and then you would expect the bending moment diagram to be like that, going down to the center, going up there. You would expect the shear force diagram to be like that, with going down like there and then going back upwards, where that distance to that distance would be equal to your 50, and then you would expect the deflected shape to be a cubic, which I'm trying to draw like that. So your deflected shape, that shape would actually be a cubic. So if we took out the compass, as I showed earlier, you would expect the radius of curvature to be pretty large. Well, it would be infinity there, but you would expect it to be pretty large around here. So these ends here, you'd expect the radius of curvature to be pretty large, which means the curvature is quite small. And then down here, you would expect the radius of curvature to be much smaller, because there would be more curvature at the center of the beam, hence the shape of the bending moment diagram. So if we just took it out and concentrated on the bending moment diagram, which would be two straight lines, so one straight line going there and the other straight line going all the way up there, and then we said what's the bending moment, say at that point under the point load. So what I would do is I would draw one arrow like that, and then one arrow like that. Okay, so if we now covered up half of it, so we said what's the free body diagram from A, so let's call that A, call that B, and call that C. And we said what's the free body diagram from A to B, that would be the free body diagram, and that direction of the bending moment, which would be in the anti-clockwise direction, which would be opposite to that force trying to rotate it round. And then if we did the same thing on the other side here, that would be the direction. So it doesn't matter if you get the arrows in the wrong direction, the maths will take care of it and it will come out negative instead of positive. Okay, so that's the first question. Just give me a second. So as we called it before, anything with the bending moment diagram below the line would be called sagging, and if the bending moment had been above the line, then it would be called hogging. Okay, and as we said, the bending moment is plotted on the tension side, so the bottom side, which you can see here, or if you take this rubber, you can see if I try to rotate it round there, you can see that side there, that side there would be in tension, so you're being consistent with plotting the bending moment diagram on the tension side, which you can see there. And right here, maybe I'll try and illustrate the radius of curvature. So if that had been the deformed shape going round like there, then when you get down here, the radius of curvature is much smaller. So there would be less curvature here. So there would be less curvature there, and there would be more curvature there. Okay. So next question is simply supported beam loaded at midpoints. So in this one here, the bending moment diagram would go down like that, and then after that it would be constant over there, and then it would be going up like there. Okay, so that would be the bending moment diagram. The reaction there, that would be 20, that would be 20 upwards down, 20 kilonewtons there and 20 kilonewtons there. So the shear force diagram would go 20, drop down to 0, and then go back up here, and then go like that, back, and then go back up there. So that would be the shear force diagram. If you can't quite make it what I'm doing here, just look at the solutions. Okay, so this line here would be 0 shear. Okay, so constant bending or 0 shear. Okay, so this line here, 0 shear, and the bending moment would be constant along that portion there. Okay. Calculate the maximum longitudinal stress on the beam given the profile at the bottom, assuming that the beam is loaded on its strong axis, which basically means that it's bending around that axis, which would be the strong axis, compared to that axis, which would be the weak axis. If that's not obvious, then just do the calculation for the second moment of inertia, and that, again, as I said, there would be a solution for that in the drop box showing you how to calculate second moment of inertias. So if we now look at the beam here with two loads at load point, I don't expect it to be clear here, but the radius of curvature for the deformed shape around there, that would be expected to be constant. So if we went, say, to the midpoint there, which would be there, we would be able to say that's how that beam would want to be bending around there, because the radius of curvature would be constant. So let's try and tidy that up a bit. So the deformed shape may look something like that. So I'll get rid of the bending moment and shear force diagrams, and I'll try and show that there. Okay, so let's get rid of that. So what we're basically saying is that the radius, that because the bending moment there would be constant along that portion, that would have a radius of curvature that would be constant around there. Okay, so the radius of curvature, if it's going to be drawn like that, it would look like that. And then so radius of curvature up there. Okay, so the curvature would be constant here, so curvature constant, bending moment constant, radius of curvature constant between those 2 points here, because the bending moment is constant, and then we would also say the shear force would be equal to 0, which it is. And then here the curvature would be 0 because it's at the end, so curvature 0 as it was there because it's a pin, and along the hair again curvature 0. And then here there would be some curvature here, but not as much curvature as there is here. So again, I'll try and illustrate it on the model. So I think you can see the biggest curvature would be between my 2 fingers. So we could say that the radius of curvature here would be bigger than the radius of curvature here. Okay, so the radius of curvature here may be something like that. Okay, and obviously the radius of curvature would be changing because the bending moment diagram is changing, but the bending moment diagram is constant between these two points. And when you reach the end, then the curvature is 0, which means that the radius of curvature is infinity. So draw the estimated deflected shape, calculate the maximum longitudinal stress at the bottom. So to get that, you would just be using stress is equal to bending moment along that portion there. Sigma equals m times y, which would be, in this case here, 250, because it would be that distance from there. So that would be 250 sigma and I, and you would get your I from the calculation of the second moment of inertia, which again I show in the Dropbox solution. So from there you would get a maximum stress of newtons per millimeter squared. So that would either be at the bottom tension side, so it would be that value in tension, or that value in compression. Okay, and this is just a recap from what Quincy and Lucas would have covered with you before. Okay, so let's move on to the next one, which would be this guy here. So we've got a steel frame loaded by a point load hanging off its ends. Draw the shear force diagram, draw the bending moment diagram, and oops, just give me a second. Draw the bending moment diagram, and what's the maximum axial stress? And remember to include the effects of the axial force. So you've got your structure like this here. So this is a fixed end, and this guy here, see, it's completely plain at the bottom, which means it's just a joint, but it's not fixed into any of the pegs here, of course. So let's get this set up there. So we just join that in here, and then we just join that in there. Okay, so I'm now sticking a load on at the bottom, and that's what you can see for the deformed shape. So you can see that is the deformed shape. You would probably be able to see that the radius of curvature is constant from here to here. So depending on how I did the deformation, oops, let's try it even more. Let's try it like that. You could probably see that around there, that is constant curvature. Okay, that's constant curvature over there. And you can see this guy here, The bending moment at the end is obviously going to be 0 because it's a free end, and then it would just increase up over here to the maximum value. And we see here that that side's in tension, so that means the outer side's in tension, which means the outer side here must also be in tension with the same value. So let's have a look at what we've got there. So this end here is fixed, and then you've got your 15 kilonewton force. So if we said let's replace this guy with a pin, so with a roller, so we replaced it with a pin, sorry, not a roller. We replaced it with a roller, and then we put the load on, you would see that this guy here would rotate. So therefore, in order to get it back, you would have to apply an anti-clockwise moment to get it back to 90 degrees, or you can see there's an angle there, and I'm having to rotate in that direction, which then tells you that that must be the direction of the reaction moment. Okay, obviously to be in equilibrium with the 15 kilonewton load. So we'll have that, and then we'll have the 15, and then up here there would also be a 15, and then the horizontal force would be 0. So there wouldn't be any force there. And as you can see, it needs anti-clockwise moment. So this is the reaction that I'm drawing. This is the reaction moment that I'm drawing, and the reaction moment must be 30 kilonewton meters. So here we've got the bending moment diagram. So I'll sketch the bending moment diagram there, and then I'll sketch the shear force diagram here. So the bending moment diagram first, constant curvature here, that being the tension side. So bending moment diagram, bending moment there has to be 0. So we look back at this one here. I'm going to keep that locked in with my finger and bend that one down there, and you can see that the top surface here is in tension. Okay, so that would show that bit there. Shear force diagram. Well, the magnitude of the bending moment diagram is of course going to be 30 kilonewton meters, and you could sort of see, you could turn that round there and put the arrow on, so the whole thing is going round, and then the bending moment diagram is plotted on the same side as that arrow, which is why the arrow, if we were to plot it here, that bending moment there would be your 30 kilonewton meters, which would be the same direction as the reaction, and then that would be 30, and then that would be 30 kilonewton meters. So for the shear force diagram, we can see that the force here is going to be 0. So the reaction in the vertical direction is going to be 15 kilonewtons, of course. 30 kilonewton meters like there for the reaction, and the horizontal reaction, of course, is going to be 0. So when we draw the shear force diagram, I'll draw a double line now. I'll draw a double line there, and the shear force is going to be 0 for there. For up here, moving from left to right, you could sort of transplant that 15 kilonewtons up to the top there, so that it's in equilibrium with there. 15 kilonewtons, and then so the shear force diagram will look like that, which I'll draw there and show that as 15 kilonewtons. So 15 kilonewtons as the shear force diagram. Okay. So the question now says, what is the maximum stress going to be? So you're going to have to work out the second moment of inertia of that, then the second moment inertia of that cross section, and it's 900 by 900. So 1 over 12, 900 times 900 cubed. So I of that is equal to 1 over 12 times 900 millimeters times 900 millimeters cubed. And that's going to work out to be 5.468 times 10 to the 10 millimeters to the fourth. Let's now draw the axial force diagram. So we've got that 15 going down there, 15 kilonewtons, and then the axial force, this guy is going to be in compression because you've got the 15 kilonewtons up there as the vertical reaction. So this guy here is definitely going to be in compression, and if you remember from the lecture, we would show the compression force like that. So it's going to be compression of 15 kilonewtons, of course. So the maximum stress is going to be right at the base. It's going to be here, or it's going to be along the length of the column, and then you would be saying the stress is equal to the axial stress. Well, the stress is going to be equal to the axial stress, 15 kilonewtons divided by the area, 900 by 900, plus the bending stress. Of course, we're working out the stress at the outer side. So the axial stress is going to work out to be 0.019 newtons per millimeter squared, and then the bending stress, you'll get the bending stress is going to be equal to sigma equals my over I. M is the bending moment. Bending moment is 30 kilonewton meters. The distance this time here, since it's like that, would be that distance there, which would be 450 millimeters, and then you divide that by I, which you've already calculated, and so you'll get the two stresses which could be added together, and so the bending stress would turn out to be 0.247 newtons per millimeter squared, and then the maximum stress would be the sum of those two, which would be 0.266 newtons per millimeter squared. And as I said, you can get the solution on the Dropbox, and in this case here, I think I've given both the YouTube solution as well as let's wait for this one to come through. So I've given that solution there. Okay. One thing to note is that that remains at 90 degrees, of course, because that's the joint. So you can see here when I bend it round, not bend it when I apply the 50 kilonewtons at the end there, that angle there remains at 90 degrees. So that deals with BD3. Now let's have a look at the next one. I'm not going to do the next one here, but you can check the Dropbox, and it uses method of sections, method of joints, and using method of sections, method of joints, you're able to, well, firstly you've got to work out what the reactions are, and of course that horizontal reaction is going to be 0. So you work out what the vertical reactions are. So I think that works out to be 12 kilonewtons, and that one works out to be 18 kilonewtons, just by taking moments and working out what the reactions are. And then after that you use method of sections, method of joints, and then you would be able to work out the force in each of these members. So according to the solution, member AB, which would be that one there, that would be 6.93 kilonewtons in compression, and sigma AF would work out to be 13.86 kilonewton, and that would be in tension. Okay, so tension, you would be showing it like that, and then compression, you would be showing it like that. So just make sure that you're okay as to how to calculate the force in each of these members, and you'll need to know how to do that when we get to the part of the course that deals with virtual work, because then we'll be using the virtual work method to maybe work out the displacement at that point, or the displacement at that point, and you'll need to be able to do that calculation in order to do that. So here we come to a portal frame. So this is number 5 here. So we've got a portal frame there, and in this case here with the portal frame, it's got the bases are fixed in, so you can see the shape there, and then I've got another solution there with the YouTube, where there's a YouTube link where I probably talk about it in a bit more detail. So let's have a look first at the portal frame. So this guy presumably would be a fix. So we would look for, so put that one there, and then this one here, that would be a joint there, that would be another joint there, and I hope I've got a piece that would make it go down here. So we've got I think I took the wrong one, so that one might be it. So this one here, so remember these joints are at 90 degrees. I don't think I've probably run out of the piece to turn that into a roller, into a fix. So if you just bear with me, and we'll just say that one is like that. Okay, so I'll stop that moving horizontally with my finger. Okay, so we show the load coming down here. So from there you can see what the deformed shape of the frame is, and remember when you look at this, these joints, they do move, of course, but if the load is exactly right in the center, then the frame is symmetrical, and so the frame wouldn't want to sway due to symmetry. Okay. So note at the bottom here that that one stays at 90 at the same angle that it was coming down at, so you can see how it curves round. Now, if you imagine that my finger wasn't there, then you could probably get the feeling that might want to, that being on a roller, sort of, it would be able to move from left to right. So let's just try and tidy that up there. There's a bit of friction, but if I move it like that, you could probably see that would want to move there, and then to get it back, I would need to push it in. Okay. So let's draw the shape of the bending moment diagram, and then draw the deflected shape. So let's start with the deflected shape, because we can see that from the kit. So we'll assume that these points don't move because of symmetry, for the reasons that I've just explained. So you could expect the deflected shape to be something like that, and then that angle has to maintain at 90 degrees as we've described. So that would have to go out like that, and it would just keep on going out, and then it would have to be brought back in like that. Okay. So if we now, so I'll keep my finger here so this end doesn't move, and concentrate on the bottom of the column there. I hope, well, I'll put more load on, and you can probably see, with an exaggerated load on, which of course that is, you could probably see that's the tension side, and you could probably see that that side's the tension side there. So still coming out at 90 degrees, but you could probably see that that side there is in tension. So the bending moment diagram, of course it's symmetrical, so so it's symmetrical, so you would expect, you could see from the deformed shape that that's going to be the tension side, and then you can see from the deformed shape that that's going to be the tension side. So the bending moment diagram is probably going to be something like that. Oops. So just make it. The bending moment diagram is probably going to be something like that. Okay. So just imagine that's a line of symmetry. So on the left side I'll show the deformed shape, and then on the right side I would show the bending moment. So you would expect something like that. Oops. Whatever the moment is there has to be the same as the moment here, so I've not drawn that quite to scale, so I'll do that there. Alright, so the bending moment diagram, so I'll give that a bit of shading so you can see the bending moment diagram there. Okay, and then so this would, the bending moment is plotted on the tension side, so you can see the tension side there. So this side here, if it was deforming round, that would be like that. So that would this side, the inner side here, remember that's a mirror. The inner side here would be the tension, so the bending moment is shown on the tension side. If I now wanted to see which way round, which way it would go, let's replace this side here with, let's replace this side here with, let's replace this side here with a pin. So again, I'll lock it in by keeping my fingers there so that it's still coming out at the 90 degrees, which you can see there. And I'm having to apply a moment in the clockwise direction. So my moment is clockwise to get that back to 90 degrees. So my moment is clockwise, so the reaction there is in that direction, and by symmetry the reaction on this side here would be in that direction. Okay, so and then the vertical, or the axial one, would be P, P over 2, and then P over 2. Then if I replace that guy there, so with this one here, so what we had originally, so as I apply the load down, you could probably, this guy would want to kick out, so the reaction needs to be going in there. The reaction needs to be going in this direction here. Oops. Okay. And so equal and opposite on both sides. So there would be a reaction there, and there would be a reaction on that side there. Okay. So draw the shape of the bending moment diagram, don't need the magnitude. So you obviously can't calculate the horizontal force at this stage, but in as we progress through the course, I'll show you how to work out this horizontal force. So obviously equal and opposite on both sides. And then it says to repeat the question with the UDL instead. So if it was a UDL, you could say the UDL it's not the same as a point load, so maybe the UDL would be better approximated by more fingers pulling it down to spread the load over, as you can see there. But if you were doing it with the UDL, then the bending moment diagram, let's just draw that, we'll draw the bending moment diagram, which would be for the beam, it would be like that. So instead of it being a straight line, it would be 1 power up, but for here it would be the same. It would be the same shape. Okay, so that would be for a UDL, and with a point load. Oops, so I just showed the UDL there, and then for the point load, it would be more like that, as we've already discussed with straight lines. Okay, and of course the same thing would apply to the deflected shape. It would be 1 power. It would be 1 power up. Right. So in terms of the free body diagram for the column, so that is this is the bending moment diagram. Now, if we said we would take it, if we would make a cut, and then that cut would just be a hair's breadth above the base, so just a bit above the base. So I'll just draw it a bit above the base here. So that would be the bending moment. Okay. So if it was just a bit above the base, then that value and that value would be the same. And then, as I said, the technique is to draw the head or the arrows of the bending moment within the section, and you can see that this is anti-clockwise, and the reaction, of course, is also in the anti-clockwise direction. So from there you could work out that one there. Okay. I'll just make a point there that one where the bending moment is 0 is going to be what's known as the point of contraflecture. So if you look at the past exam questions, they tend to ask you to indicate the points of contraflecture. So that there would also be a point of contraflecture. That's where the bending moment is 0. So here that would be point of contraflecture by symmetry, and then down here that one would also be the point of contraflecture. So if you had a look at it here again, you put the load down, you could see, let's see, okay, so we put the load down there, so we can see tension there, we can see tension there. So there's somewhere that it's going to switch from tension on the top to tension on the bottom, or the bending moment is 0, and that would be known as the point of contraflecture. Okay, so let's move on to the next example. So the next one would be BD6. So what happens with this? So what happens with this one here is that you could split that into 2 bits. So you could split that into two problems. So the first problem is with the UDL, and then the second problem would be that one there with the So this is an externally applied moment, it's not a bending moment. So we're using the theorem of superposition, which basically says everything is elastic, and we're adding on the effect of that to that one there, and that would give you the total value. So now if we go here, so again your pin and your roller. So let's deal with this case here first. So that's your externally applied moment or a rotation. So we're making a rotation at that point there. So we're making a rotation here in the clockwise direction, or a moment in the clockwise direction. So that one would go like that, so you could see the deformed shape, that side being in tension and then that side being in compression. So the shape of the bending moment diagram, well, we've seen the deformed shape there, so we can see the shape of the bending moment diagram would be like that, and then it would come down here, and then it will go up. So the precise values, of course, would depend on the reactions that you've calculated. So if you've applied the 8 kilonewtons here, you would probably find out that that reaction there is 0.8 kilonewtons, and you would probably find out that that reaction there is 0.8 kilonewtons. And when you plot the bending moment diagram, you would find that that distance there, from there to there, that would be 8 kilonewtons meters. Okay, 8 kilonewton meters. So that would be the bending moment diagram. And then for here, you've put some curvature down. You put some curvature down on this side here, but left nothing on the other side. So if you did that, you would probably find that the bending moment diagram would look something like that, and then after that it would go straight up. So that would be a straight line, and that would be a line with some curvature. And under that, the 3 kilonewton meters, you would probably find that is 7.65 kilonewtons, and you would probably find that reaction there is 1.35 kilonewtons. And the point is that you would then be able to add that bending moment onto, you would be able to add the two bending moment diagrams together to give you the final solution. So the final solution, which I would draw here, the final solution would be something like that. And what you would do is you would work out that bending moment at that point, which would be sagging, and then you would be able to work out what that point is, and what that point is just by basically adding the two bending moments, adding the two bending moment diagrams together. And so that would be 1 plus, so I'll just try and sketch that one there, which would be going down. So you'd be adding the two together, and that one is above the line, that one is below the line, so it would cancel each other out. So that one may end up down there. Okay, so that point would be there. That one is a bit above. This one is quite a bit below, so that would take that up down there. So you're just basically adding the two bending moment diagrams together, and you would probably get, just continuing that going round, it would be going all the way up there, all the way up, and then down, and then back down there. Okay. So let's get so the point is you would be using the theorem of superposition to enable you to basically add the two bending moment diagrams together, and then that will give you the final bending moment diagram. And then you can use exactly the same technique for the reactions. So the reaction here would be 7.65 minus 0.8 upwards. So it would be upwards 7.65 minus 0.8. And then the reaction here, I think both are acting in the upward direction. So it would be 1.35 plus 0.8 kilonewtons. Okay. So you can check out the solution on the Dropbox for both the bending moment diagram as well as the shear force diagram. But as you can see, we've split it up into the two load cases, solved them separately, and then added them together by the theory of superposition. And then the final problem here, which would be this one here, which would be this example here. So here we've got one force, so we've got one force there of the 5 kilonewtons, fixed column base down here, and then down here we've got a UDL. So that W is an expression for the UDL, which would be curved in this case. So what do we do for this one here? You could say, look at that shape there, and you could work out where the center of gravity of that shape was, and that would be where you could say the equivalent force is applied. So you could split that problem into that one there, and instead of having the UDL, work out the centroid of the UDL, and apply the force which would be the area under that curve to here. Okay. So you would probably have to do that by integration, work out the position of the centroid, and then you would be able to work out what the reaction is at the bottom. So it turns out that that's going to be 36 kilonewtons for the equivalent one here, with a distance away from there that we can calculate. So I believe I calculated that distance to be 0.813 meters. From there you can work out what that force is, which turns out to be 29.25 kilonewtons. You can work out the horizontal force, which would be 5 kilonewtons, and then you could work out the direction of the moment reaction, which would be 5.73 kilonewtons. And then after that, once you've got the bottom bits, then you would be able to go back and you would be able to draw the bending moment diagram, and then to calculate the bending moment diagram as you go along there. So let's have a look here. BD7. So I stuck my solution here, where I worked out the area, where I firstly worked out the area under the line there with a switch of axes, drew the bending moment diagrams, and then from there I showed that when you have a look at the joint, there, so if you have a look at that joint, that's obviously going to be 10 kilonewton meters. And then when you have a look at that joint there, so that one would be around there, going here. And then that one would be 19.25 kilonewtons. And then when you looked at that portion there, that would be a bending moment going around like there at that joint. And that value would be 29. So let's draw it like that. So that value would be 29.25 kilonewton meters. So if we zoomed in on that joint, remember we put the arrowheads on the same side of the bending moment diagram. If we zoomed in, then we would see there would be a 29.25 kilonewton meters. There would then be on that side down there another one which would be like that, which would represent the 10 kilonewton meters, and then from the bottom one up you would get another one which I draw slightly bigger, kilonewton meters, and then you could therefore see that that joint is in equilibrium. That one plus that, these two are both in the same direction, that's in the opposite direction, so the net moment is 0. So that was a check you can do right at the end to make sure that you've done the calculation correctly. So problems like this one here, well, equilibrium of the joint, which we demonstrated here, but problems like this one here, when you've got a strained shape, again, we'll have a look at the similar ones when we look at virtual work and later on in the course, and when we look at the flexibility method. So that ends this one here. So beams and deflections. So now I've got a series of beams that we can come up with. So let's start with the simply supported beam. Drop it down here. So this one here, let's get down there. So again, beam, let's just take a beam here, put the load on there as we've seen. That becomes the tension side. So we can draw the deflected shape like that, which would be the same as here. The reaction half here and half here. Shear force diagram following the direction of the actions, which would be that and that and that. So that would be 2.5, 5 and 2.5 kilonewtons. So the shear force diagram would down there, go back up, and then that distance there, of course, would be the 5 kilonewtons. And then the bending moment diagram would be like that, okay, with that being consistent of being on the tension side. So that's the first one, simply supported beam with a central point load. Now, when we've got this one here, so I think this one here, maybe I can demonstrate that with something like here. So it's still what's known as statically determinate. Maybe I don't have quite a long enough one. Maybe that one's better. Okay. So this is another example of a pin, sorry, of a roller. You can see that the thing can slide in between here, but it can't go up and down. So that if your beam is long enough, we can use one of these here. So this one go down like that. So we can see that's the tension side going up. Bending moment there is 0. Radius of curvature is infinity at that point, and curvature is 0. Here there's some curvature. You can see it curving round. So we can see there's curvature around here. So the radius of curvature would be maybe somewhere around there. And then back here at the pin, we can see that the bending moment is 0. So let's try and sketch that. So deflected shape. So I'll just draw it here. Oops. So I'll just draw it here. Okay. And then just show that as being the tension side. Okay. And then here I could say bending moment equals 0 or curvature equals 0, since bending moment is proportional to curvature. Bending moment is equal to 0 at that point there. So the reaction, so that's coming down, so there would be a reaction there. So we would show a reaction there, which would be going upwards. Now if I took this out and then I put my load down there, you would see I've had to move that downwards there to get back to that point. So therefore the reaction is going to be in that direction. So we've got a reaction in that direction there. Oops. So the shear force diagram would look something like that, going down, and then that going up, and then that going back down there. So perhaps I might want to show that that force is twice the size of that one and that one to explain that distance there. Okay. And then finally we get to the bending moment diagram, and so the bending moment diagram would look like here. You can see the tension is going all the way up here, okay, and then down here that side's in tension. So the whole thing's in hogging. Bending moment there is 0, bending moment there is 0, and then bending moment is maximum over here. So we would get a bending moment diagram like there, with the whole thing being in tension. So let's have a look at the next one here, which would be number 3 in the set. So I'll get rid of that there. Okay, so that's the problem there. So we started off originally with the roller, okay, and then an internal one, and then another one, and here I might use that one there. Okay, so this and this are the same. It allows rotation around there and there, but it doesn't allow it to move up or down, and this one doesn't allow it to move up or down, but you can have sliding here over here. Okay, so in this one here, contrast it to this one here, where there's the load. So I've now put an additional support. So this one has now become your statically indeterminate case. So this one here is still statically determinate, which means you can just use statics or NGen 121 to work out the values of the reactions. This one here, because of the additional support, it becomes statically indeterminate by 1, because we've introduced one extra piece. So before it was like that, still statically indeterminate, still statically determinate, with the force, let's say, going down there. And now I've added on another boundary condition, so it's become statically indeterminate by 1, okay, which would be that piece there. So here the load goes down there, so tension there, tension there. You can see, if I hope that, as I put the load on, of course the whole thing slides across, and hopefully you can see that there is still some curvature over the internal pin. So this pin there, there's curvature. So if there's curvature, oops, put the compass there. So if there's curvature, that basically means, if there's curvature, that means that there's a radius of curvature, and therefore, which you can see, might be able to see there, Okay, so there's a radius of curvature, so it's curved under there, which means there's a bending moment. So a lot of students sometimes think that because that's a roller, they say that and that bending moment there is 0, so the bending moment there must also be 0. But as we can see from the prop, there is curvature. So the deflected shape, let's start here. So that one doesn't deflect, that one doesn't that one doesn't move downwards or upwards. This point doesn't move downwards or upwards, and this point doesn't move downwards or upwards. But of course, these two are allowed to move in these two directions, otherwise you're getting stressed, you're getting tension action or catenary action in the beam. And we would maybe be able to predict that that point where the load is being applied, that point may be going down there with some deflection. And later on I'll show how you can calculate that deflection. So we would normally say the deflected shape plots a cubic. So I would just say just try and draw a smooth line between those points that we know, and then that would be your deflected shape. And maybe it might be worth trying to make that a bit smoother. Okay, so maybe something like that. So we can see there, we can see at that point there that there is going to be some curvature, and the curvature is likely to be like that. Down here, maybe the curvature, so the radius of curvature there, maybe the curvature there is, the radius of curvature is bigger. And then down here, maybe the radius of curvature would be more like that. Okay. So let's just draw 2 arrows there to show the radius of curvature at the points. Okay. So bending moment is proportional to curvature, and when we do a bending moment plot, we're effectively just plotting curvature. So let's have a look at the shear force diagram, or let's have a look at the reactions. So I'll get rid of that. Okay. Now go back here. So I stick my force here. Now, if that had disappeared, and I stick that there, okay, you can see that point has gone down. So the reaction must be upwards to restore it. Yeah, so that must be an upwards reaction at that point. If we put that there, then that must also be an upwards reaction to go back to point of 0. And then for the last one, if we put that there, and then if I remove that one and put my load on, you can see that point's gone upwards, so the reaction must be downwards. So from there you could deduce the direction of the reactions. So I could deduce that the reaction here would be downwards. The reaction here would be upwards, and it's probably going to be quite a large reaction because it's very near there. And then the reaction here would be up there, okay, which would be a bit smaller than that value. So the shear force diagram, that's going down, so I would maybe draw a shear force diagram like that, then go up, and then go down here, down again, and then here, and then up there. So maybe that one is not exaggerated enough because I wanted to show that. So maybe that would go a bit higher. So remember, the size of that is the size of that, the size of that reaction is the size of that, and the size of that is the size of that. So So probably I need to show that a bit bigger. And of course these are just straight lines. And then the last bit is the bending moment. So tension, tension, tension. That's also in tension there, as we can see. Bending moment would be 0 there, 0 there. Bending moment is going to be in tension at that point there. So that one is coming downwards. Okay, so if so if I took a shorter piece, so we can see that force is coming down. So I took a shorter piece and then put that down, which is where that reaction is downwards. So here I'm trying to map on the downward reaction, okay, by putting it downwards, and the curvature on that side there. And of course with the cantilever, the bending moment would be triangular, just increasing the further away it gets from here. So the bending moment diagram would look straight line going to up there. So bending moment plotted on the tension side, and then you would expect the bending moment to go down like there to be a maximum under that load there, and then back up to 0. So in terms of that one there, upwards, so let's turn that around, upwards, so we've got that going upwards, so that and that same free body diagram as we move across, so tension on the underside, so which is what we've shown there. So tension, 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 and that bending moment would be equal to 0. So that's a 2-span beam with a point load there. So while we're on this, if I had a simply supported beam with that load acting downwards, of course the bending moment diagram would be like that. And if that was P, that drop there would be PL over 4, as we calculated before. Now if you did a dotted line from here to here using theorem of superposition, you would find that that drop there is also equal to PL over 4. Okay. So maybe I'll tidy that up. So the distance from that point to that point, or that distance down there, that is going to be PL over 4. And later on we'll be making use of that. So that's just part of theory of elasticity or theory of superposition. So we've done this one before already, so no need to do that one again. But now this one becomes part of set 2. So set 2, question 1. So what we're doing here is, instead of it being simply supported, a simply supported beam, what we're doing here is that we are turning. So originally here with the point load, so I'll go back to that one, with the roller, so that allows it to roll there. So down here you can see there's a rotation there, so you can see that rotating and you can see that rotating, and now I'm saying you put that up there so that that maintains at its original angle, or I don't allow that angle to move, and that's how it's going to look. Okay, and you can get the same effect using this guy here, which is a fixed support. So that pegs in and that clicks into there. Oops. And then that guy doesn't rotate. So how does it look? Deflected shape. So you can see rotation is allowed there, so bending moment at the end is 0. There will be a bending moment here at that side there. So deflected shape would look something like that. And then I'll do that to show that it's still at 90 degrees. Shear force diagram. So this one here is going to have a bigger reaction than that one there. So that's for the reactions. So the shear force diagram would look something like that, going back up there. And then the bending moment diagram would look something like here. That being the tension side here, and then that one coming down there, and then from there going all the way up. Okay, so tension, 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 and then that would be the point of contraflexure. So this is what's known as a propped cantilever. Next one here is what's known as so it's drawn like that, but technically speaking, because we don't want to get that catenary action in the beam, it's actually, one end is actually assumed to be able to slide, which is fine. This way. So central point load, symmetry of course, so we can see that the thing is going to be symmetrical. So deflected shape would look like that. 90 degrees, 90 degrees, tension, 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 tension. Reaction, half the reaction there, half the reaction there. And then if you remember, if that had been a pin, it would have wanted to rotate like that. So the reaction must need to be, the reaction moment must need to be acting in that direction there. Okay. So if you just replaced this with the pins that allow rotation, we can see that we would need to. Okay, I might as well just demonstrate it. You can see that if that end had been pinned, load coming down here, you can see there's a rotation. So I would, if I wanted it to remain there, so lock it in with my finger, pull it down, I can feel that I'm having to rotate it in the anti-clockwise direction. So anti-clockwise for that reaction, moment reaction, and then clockwise for this one here because of symmetry. Shear force diagram would look like that, of course, because the shear force diagram is unaffected by the moments. It's just to do with these lateral actions. Bending moment diagram would look something like that. With that moment being the same as that moment. So if we drew a free body diagram of half of it, just a bit away from the support, then that one of course would be like that, and then that one of course would be like that. So that would be, if that was A, B, C, that would be the free body diagram of AB. Not forgetting the shear, of course. Okay. So this is known as a fixed-ended beam, and these are the moments generated when both ends are fixed. So let's have a look at this one here. This is a UDL, which we can see here. So, of course, as I said, I can't demonstrate a UDL using this, but I just pretend it's a point load, and then from the point load I get the shape, which would be triangular, and then I will add a bit of curvature into it, sort of raising the power of x up by 1. So that means that the deflected shape would be like that. The reaction, of course, would be the same as before. Bending, the shear force diagram would go up, and then here up again, and then at the center it would be 0, so that would be the shear force diagram, and the bending moment diagram. So there's very little that you need to remember, but we remember PL/4, and we remember that the bending moment there is WL²/8, where W is the 10, L is the length of the beam, and the number 8. And you can derive that, of course, as we've done in the previous examples. So let's look at the next one. So this one we've done before, simply supported beam. And this leads on to set 3. This one here, the trick with this one here is that you need to separate the load. So firstly, you do a beam like that with the UDL there, and then you add that onto another problem where you've got that load there. So you're separating the problem into, firstly, that, work out the bending moment diagram, and then the other bit where you work out the effect of that bit there. So let's start with the bending moment diagram in this case here. So bending moment, you would expect it to go up there, and then I might do a dotted line down to 0, PL/4 for that, drop it down there, which would be PL/4, and then just continue to do that. And that would be the bending moment diagram. And if I drew a dotted line from here to up there, and if at the center of the beam, I would expect the drop to be WL²/8. So I would expect that distance to be WL²/8 later on when we calculate it. So that would be the deformed shape. Shear force diagram, I would expect that reaction to be upwards, which it would, so the shear force would go up there. I would expect that reaction to be quite large and upwards there as well, and then I would expect this reaction also to be upwards. So the shear force diagram may be something like that. And then going up here, going down here, going down there, and then going back up. So I would expect that one to be maybe something more like that for the shear force diagram, with that being upwards, that being from there to there upwards, that one downwards, so from there to there, and then this one upwards from here to back to 0. And then as for the deformed shape, you would expect it to go something like that, and then down here, and then back here. So I would expect from here, we plot on the tension side, so I would expect there to be curvature here. So I would expect there to be curvature there, I would expect there to be curvature here, and I would expect that one to be the tension side there with curvature. So you can see that in this case here I started off with the bending moment diagram and put in the bits and pieces as I went along. So set 4, which is the statically indeterminate case, so this one's a longer one. So I've got this piece here, which is a bit longer. So 1, 2, 3. So if I had one piece there, one, two, three. So I've got 3 bits here. So apologies for this, it would have been a bit easier in the classroom. Move that over there, so 1, 2, and then this piece here, 3, so that would sort of maybe move that a bit there. So I've got my 3 bits. So I've turned my UDL into a point load, as I said. Okay, so that would be down there. So okay, let's deal with the easy one first. So get rid of that. So put that there, and you can see as I do that, that this end here has gone downwards. Yep. So that end there has gone downwards, which means the reaction has to be upwards. So the reaction of this one here at the end is upwards. Now remove this one here and put it there. Now you can see that the deflected shape in the middle has gone upwards, which means the reaction has to be downwards. And the last one would be if I remove this guy here. So if that guy there's removed, I put my load on, you can see where he was, it would have been downwards, so the reaction must be upwards. Okay. So you can sort of work out which, so there's one left to do. So if this guy has disappeared and the load was acting downwards, you can see the reaction would need to be upwards. Right. So with those bits of information, let's go back. Let's again, we've drawn the deflected shape. So let's have a look. Let's start with the reactions. So of course you would expect this reaction to be quite large here because it's quite near to where we are, and that would be acting upwards as we've shown, because if this end had disappeared then this beam would be going down, so the reaction must be upwards. If this one disappeared, that would have curved down, so this must be going upwards. And you would expect that one to be larger than that one there. And then this one, if this one had disappeared, we would have expected it to be up, so the reaction must be downwards. So I put a reaction there downwards. And then this guy at the end here, if that guy had disappeared, I would have expected the reaction, the deformed shape, to be like that, so I would have expected that to be upwards. And of course, bending moment is going to be equal to 0 for the cantilever bit, since there's no load acting on it. So deflected shape, I would expect these points here to be 0, maybe, and of course at the bottom of the UDL the biggest. So it would then have gone like that down there. Then that would have continued to go on upwards, and this guide would have been straight because there's no bending moment there, so whatever slope or gradient there was there, that would just pass on that side there. So shear force diagram, you would expect that to be up, and then you would expect that to be down. This one being bigger than this one, because there's more beam stiffness here. This is just at the end. Then that would have gone up a bit, that would have gone down, and then gradually go down to 0. Okay, which we can see there by the relative dimensions of the arrows. And then the bending moment diagram, you would have expected that to go something like that. You would have expected that to be like that, and then bending moment at that point would be 0, which is at the end, so a straight line would be like that. Okay, so that's what you would have expected the bending moment diagram to be. So you might remember in class I talked about the left finger. So this is my left finger on the bending moment diagram. So the left finger is below the right finger, and the left finger is below the right finger, so on the shear force diagram it's below. Here the left finger is above the right finger, so on the shear force diagram, because the left finger is above the right finger, it's above the line there. Okay. And I think I'll leave you guys to finish the rest of these yourselves, and those solutions for these are on the Dropbox. Now let's move on. Moving on here, bending moment diagrams of frames. We've talked about these. If you're confused, this is how a student explained it. As I've often said, I don't really mind if you want to call it positive or negative, but I prefer to call it hogging and sagging. Sagging and hogging for the bending moment, and maybe for the shear force above and below the line. But this is what a student has explained, and I don't really mind whether you call one positive or negative. It will come out in the wash in terms of the calculations. And then some typical questions: radius of curvature, deflected shape, and direction of the bending moments, and yeah. Okay. So what we'll do next is that we will have a look at some of one of the previous class tests. So I'll have a look at the basic skill test from 2016, and we'll run through that one, and then I'll leave you to go through the rest of the examples and solutions, just until you sort of get a feel of beams.